Cations and anions salt pack into lattices. We talked about simple cubic, body-centered cube, hexagonal closed packing, and finally face-centered, which is equal to cubic closest packing. How can you predict from the structure of and the size and charge of the cation and anion into what type of cell it might pack? How can you predict it? Well, it turns out for us mostly, the unit cell will be defined by the anions, which in general are larger than the cations. It depends obviously on the cation. So let's assume they occupy corners, faces of a unit cell, and then the cations being smaller because of charge attraction, pulling the electron cloud in, will occupy the holes. Let's briefly think about the holes that we talked about and the relative size of those holes. Let's start off with a cubic hole right here. And this might be a cation packed into a simple cube defined by the blue anions. Well, if you think about it, this is surrounded by 8 anions. And so that's 8, it's a lot. It's a lot of things that are able to get close to it, suggesting that there's a lot of space into here in which you can crowd around these anions. So the cubic hole, which has coordination number 8, is the biggest of these kind of holes. Now, using that logic, let's go to the octahedral hole. Octahedral hole, again, we have 6 nearest neighbors of opposite charge. If that's the cation inside, we have 6 anions around it. Well, that's fewer anions that can pack close to it, so that hole is presumably smaller. And finally, let's go to a tetrahedral hole. In this case, you only have 4 nearest neighbors, and that's not many, and suggesting that it's very tight quarters, and in fact, this little hole, tetrahedral hole, must be the smallest. So in terms of hole size, the largest would be the cubic, the next would be the octahedral, and finally the tetrahedral. So now if you're thinking of a given salt, like for instance sodium chloride, how would it pack? We have to consider the relative size of the cation versus the anion. Now let's consider this next slide, in which we look at a cation surrounded in some kind of structure by anions, which is that these are the most stable. And it turns out this is here because we have closest contact, and if you think about it, we want closest pack, and we saw that that's nature's way of being most stable. And here, the cation completely fills this hole in this intimate contact. It's touching the negatively charged anions. This is the most stable. How about the next one? Well, the fact is, this is the one to the left. It's a little hard to see. It turns out this cation is just too big to fit into this hole, and what it's done effectively is push these negative anions away. And so, I mean, it's a little close to them, but this is less ideal than this. And the least stable of all is if this cation is too small. Now we have these anions too closely interacting, maybe repelling, and this cation sort of rattling around in here. So this becomes the least stable. So again, we have to look at the relative size of the cation and how it's going to fit into these holes. And we want closest packing as possible, intimate contact. So again, here, if we assume the cation is smaller than the anion, so either the holes we looked at. Here's the cubic hole. We said that's the biggest one. And the next biggest one was the octahedral hole, and the smallest one is the cubic hole. When you can only get 4 nearest neighbors of opposite charge near it. Well, if we look at this is the smallest hole. It turns out if we put a cation here, it's too big, it won't work. So by studying examples out there, we can see that in general, this is very general, if the radius of the cation to the anion falls in this range, 0.225 to 0.4, in other words, the cation is very small, well then it can fit into this small hole optimally, the tetrahedral hole, with the anions arranged, maybe in a face-centered structure in which the tetrahedral holes are parent. So again, this would have a coordination number 4. If we increase the size of the cation, it no longer fits into the tetrahedral hole, but it would fit into an octahedral hole. Remember, you can only get 6 anions around it, so it must be bigger. And so this is the relative size of the cation to the anion for it to fit into the octahedral hole, which has a coordination number of 6 anions surrounding it. And finally, if it's really big, 0.732 to 1, in other words, it's almost the size of the anion, well, then it can fit into the cubic hole, which is the biggest of all. And that's the case that's shown here. Actually, it's almost like a cubic body-centered cube. If this was just a metal packing, we could have another metal in here. It's exactly like the other ones, and then it would be the identical size. So again, this is the roomiest one. And if we envision again a face-centered cell, remember that we have both tetrahedral holes and octahedral holes, and the tetrahedral holes would occupy, there's 8 little mini cubes inscribed in this one large face center. I've just highlighted with red one of these little mini cubes with an anion in every other corner, and this would be in the center of each of the little cubes would be a tetrahedral hole. And of course, if I have 8 of these little cubes, there's 8 of these here as well. The octahedral holes, for instance, in face-centered, we saw there was one in the center. Again, we have, so that would be sodium, for instance. We have chloride top, bottom, left, right, front, back. And on the edge, any edge atom, if sodium was there, we would have a chloride to the left, right, back, front, top, bottom. So again, that shows you a little bit about the size of the hole, the coordination number, and the relative size of the cation that can fit into any given hole.